Let's recall that at the previous lecture, we began to discuss functional models for normal operators and more general for representations of commutative C-star algebras. And so far, we achieved our goal only in the special case of cyclic star modules and respectively of star cyclic normal operators. So let's recall our results. Our first result was Theorem 1, and this is the functional model for cyclic star modules over algebras of continuous functions. So suppose that X is a compact Hausdorff topological space. And suppose that H is a cyclic star module over C of X, over the algebra of continuous functions on X. Then there exists a positive Radon measure, mu, on X, such that H is unitarily isomorphic to L2 of X mu over C of X. So here the action of C of X on the L2 space is pointwise. So this is a functional model for cyclic star modules over C of X. And as a special case, we obtained a functional model for star cyclic normal operators. And this was our Theorem 2. Suppose that H is a Hilbert space, and T is a star cyclic normal operator on H. Then there exists a positive Radon measure, mu, on the spectrum of the operator, such that the operator T is unitarily equivalent to the operator MT, which acts on the L2 space on the spectrum. And this operator acts as the multiplication by the coordinate. So it acts by the following formula. So we observed that this result is essentially a special case of Theorem 1, because if T is a star cyclic normal operator, then we have the continuous functional calculus for T, which makes H into a cyclic star module over the algebra of continuous functions on the spectrum. And so Theorem 2 becomes a special case of Theorem 1. Okay, so these are our main results of the previous lecture. Today, our first goal will be to extend these results to arbitrary, that is, not necessarily cyclic star modules over C of X, and respectively to arbitrary normal operators on the Hilbert space. So to prove, to extend these results, we need the following simple construction. So suppose we have a family Hi of Hilbert spaces. And let's denote by H the set of all elements xi in the product of the spaces hi, such that the following condition holds. Let me explain what the infinite sum here means. If the set I is countable, then everything is clear. This is just the sum of the respective series. And in the general case, we define the infinite sum of this family as follows. We take the supremum over all finite subsets of I of the respective sums. So for each finite subset of I, we form the respective sum, and then we take the supremum. This is maybe the simplest definition of an arbitrary sum of non-negative real numbers. Here is a simple exercise. First of all, it's easy to show that if the above condition is satisfied, that is, if this sum is finite, then the sum is actually countable in the sense that xi is 0 for all but countably many indices. So this family is concentrated on a most countable set. And second, the vector space H, the set H, which was defined before, above, is actually a vector subspace in the product of the spaces Hi. Vector subspace in the product. And moreover, it is a Hilbert space. With respect to the inner product given by the following formula. So here this expression is well defined because we already know that both xi and yi are concentrated on an at most countable set. And the Cauchy-Bonnikovsky-Schwarz inequality easily implies that this series absolutely converges. And it's elementary to check that this is in a product. So the only point here is to show that H is complete. But this is proved in much the same way as the completeness of the little L2 space. By the way, if I is countable and each space Hi is one-dimensional, we get the usual little L2 space. So this space H has a special name. H is denoted by the following symbol. So similarly to the direct sum, but with a dot over the direct sum sign. This space is called the Hilbert direct sum. The Hilbert direct sum of the family Hi. Let's make a couple of simple observations related to this construction. First of all, let's observe that if each space Hi is not just a Hilbert space, but suppose that it is a star module over a Banach star algebra A. So if each Hi is a star module, then it's easy to see that their Hilbert direct sum is also a Hilbert star module over A. Is a star module over A. And explicitly, the action of A is very easy, just kind of pointwise action. So this is well defined because we know that the norm of AXI is less than or equal to the norm of A multiplied by the norm of XI. And so the resulting family AXI sits in the same space. It's easy to show that this action makes the Hilbert direct sum into a star module over A. And the second observation is about kind of internal direct sums. So it gives us a condition which enables us to identify some star modules with Hilbert direct sum of their submodules. So suppose now that we have a Hilbert star module, say H, or that H is a star module over Banach star algebra A. Well, maybe let's be H prime. So we don't assume from the very beginning that H prime is the same H as in the previous observation. So suppose we have a star module over a Banach star algebra A, and suppose we have a family Hi, a family of closed and pairized orthogonal submodules of H. And let's also suppose that their sum, their algebraic sum, is dense in H. And let's then consider the following map. A map which acts from the algebraic direct sum of our family to H, and it acts by the following rule: takes the family Xi to the sum of this family. So here in this formula, we consider the algebraic direct sum. So this map was well defined because all but finitely many Xi's are 0. So I claim that this map is isometric, which is immediate from the Pythagorean theorem. Also, it's clear from the construction that it is an A-module morphism. And the above condition on the density implies that the image of this map is dense in H. has dense image. This implies that this map uniquely extends to a unitary isomorphism. To a unitary isomorphism between the Hilbert direct sum of the family Hi and H. So in this situation, we say that H is decomposed in the Hilbert direct sum of the respective family of its submodules. Okay. We will need a couple of simple lemmas about star modules. Lemma 1. Suppose that A is a Banach star algebra. H is a star module over A. And suppose that H0 is a submodule of H. I claim that the orthogonal complement of H0 is also a submodule of H. Well, the proof is very easy. I would take any element in our algebra, an arbitrary element x in the orthogonal complement of H0, and an arbitrary element y in H0, and calculate the following inner product. So one of the axioms of a star module implies that we can write this inner product in the following way. So now H star y sits in H0 because H0 is a submodule. And since since x sits in the orthogonal complement, we conclude that this is 0. And that's it. So we have shown that Ax sits in the orthogonal complement of H0, and so it is a submodule of H. Okay, and now one more lemma. Lemma 2. Again, suppose that A is a Banach star algebra, and H is a star module over A. I claim that there exists a family Hi of closed and pairwise orthogonal submodules. Submodules of H, such that H is unitarily isomorphic to their Hilbert direct sum. So this is a very nice property. Each star module is decomposed as the Hilbert direct sum of family of cyclic. Sorry, I forgot to mention that all the submodules are cyclic. Closed, cyclic, pairwise orthogonal submodules of H. The proof is a simple application of Zorn's lemma. So we consider set M whose elements are families of closed non-zero pairwise orthogonal submodules, cyclic submodules. Of H. Clearly M is a partially ordered set with respect to the usual inclusion. And it's a simple exercise to show that this set satisfies the conditions of Zorn's lemma. This is a simple exercise. So by Zorn's lemma, this set has a maximal element. Let's denote that element by HI. So this is a maximal family of closed non-zero pairwise orthogonal cyclic submodules. And let H0 denote the closure of their algebraic sum. So this is a closed submodule of H. So we are going to show that H0 is the whole of H. And if this is not the case, let's assume for a moment that H0 is strictly smaller than H. In this case, the orthogonal complement of H0 is non-trivial. And we can choose an element in the orthogonal complement, a non-zero element. There exists a non-zero element X in the orthogonal complement of H0. And let's now do the following. Let's take our maximal family HI. And let's add one more submodule, namely the cyclic submodule generated by X. I claim that the resulting family sits in M. This follows immediately from lemma 1. So we know that the orthogonal complement of H0 is a submodule. And so if we take an element in the orthogonal complement, then the cyclic submodule generated by X is contained in the orthogonal complement. And so the resulting big family, which is strictly bigger than HI, is also a family of cyclic pairwise orthogonal submodules. Now this is a contradiction because our family was maximal. So this contradiction implies that H0 equals H. And by our second observation from the previous page, we conclude that H is unitarily isomorphic to the Hilbert direct sum of the family HI. And this completes the proof. Okay, now we are ready to prove functional modal theorem. This will be Theorem 3. This is the functional model for star representations of C of x. So suppose that X is a compact Hausdorff topological space. Oh, sorry, maybe before I formulate this result, I have to recall some notation from the previous lecture. Otherwise, it could be not entirely understandable. So let's recall some notation from the previous lecture. Suppose that we have a measure space, omega a mu, a measure space, and suppose that X is a compact Hausdorff topological space. And suppose that we have a measurable map phi from omega to X. Here, measurable means that it is measurable with respect to the Borel sigma algebra on X. That is, the pre-image of each Borel subset of X sits in the sigma algebra A. So in this case, the L2 space, L2 of omega mu, becomes a star module over the algebra C of X. Namely, the action of C of X on L2 of omega mu is given by the following formula. So we compose A and phi, and we get a bounded measurable function on omega, and we take the pointwise product of this function with f. So this formula determines a star module structure on L2 of omega mu. This module will be denoted as follows. So our main result for today states that each star module over C of X is of this form. This is the theorem about functional model of star representations of C of X. So suppose that X is a compact Hausdorff topological space. And suppose that H is a star module over C of X. Then there exists a measure space omega a mu and a measurable map phi from omega to X such that our module H is unitarily isomorphic to L2 of omega mu phi, where this module L2 of omega mu phi is defined above. Okay, so let's now try to prove this result. First of all, we combine Theorem 1. So let's recall that Theorem 1 was about the functional model of cyclic star representations of C of X. So we combine Theorem 1 and Lemma 2. So by Lemma 2, H is isomorphic to the Hilbert-Direct sum of a family of its cyclic star submodules. And Theorem 1 states that each of the summands has a functional model. So we conclude that H is unitarily isomorphic to a module of the following form. Where each mu I is a positive Radon measure on X. So roughly what we're going to do now is to combine these measures mu I together. So formally we do the following. We denote by omega the disjoint union of sets xi, where each xi is x. So we take many copies of the same space X and we take their disjoint union. And this will be our space omega. Now we have to define the sigma algebra A. So the sigma algebra A will be defined as follows. A consists of all disjoint unions of the sets Bi, where each Bi is a Borel subset of Xi. And it's easy to see that A is indeed the sigma algebra. Okay, now we have to define the measure mu on this sigma algebra. The measure will be defined as follows. We define the measure of such a disjoint union Bi to be the sum of the measures of each Bi. Sum ui of Bi. Of course, I don't claim that this sum is finite. Sometimes it is infinite. And in this case, the measure is infinite. Anyway, it's more or less immediate from the definition that mu is a sigma additive measure on A. And finally, we have to construct a measurable map phi from omega to X. We define this map as follows. We define phi from omega to X by the following formula. If little x is an element in Xi, then phi of X equals X. So this is for each X in Xi and for each index I. So perhaps let me draw a picture which illustrates this construction. So if I draw each copy of X as an interval, so this is X1, X2, X3, and so on, then the graph of the function phi looks as follows. So this is just an illustration which explains what is going on. Okay, so we have constructed all the ingredients for our module, and now we have to construct a unitary isomorphism between H and the L2 module, L2 of omega mu. To construct such an isomorphism, we introduce a suitable family of submodules of L2 of omega mu. So for each I in our index set big I, we consider the following submodule hi, which consists of all functions f in L2 of omega mu, such that f of x vanishes for almost all x outside xi. So in other words, hi consists of functions in L2 concentrated on the set xi. So it's clear from this definition that hi is closed submodule of L2 and this submodule is actually unitarily isomorphic to L2 of xi, which is just x. To L2 of x mu I. The isomorphism is more or less immediate. It's extension by zero. If we have a function in L2 of x mu I, then we identify x with the set xi, and we extend it to omega by zero. And conversely, if we have a function in hi, we simply restrict it to xi, and we get a function in L2 of x. Okay, now I claim that the sum of these submodules hi is dense in L2. This is very easy. So suppose we have a function which is orthogonal to each of the submodules hi. Suppose that f is orthogonal to hi for each I. This easily implies that f vanishes on xi almost everywhere. And this happens for each little I. If we now look at the definition of the measure mu, we conclude that f vanishes mu almost everywhere on omega. So we see that the orthogonal complement of the sum of this family is trivial. Or equivalently, this means that the closure of this family is L2 of omega mu. It is also immediate from the construction that these submodules are orthogonal to each other. So combining these observations, we conclude that L2, the module L2 of omega mu phi, is unitarily isomorphic to the Hilbert direct sum of the family hi. But we already know that each I is unitarily isomorphic to L2 of x mu I. This follows from this formula. And we already observed at the very beginning of the proof that this Hilbert direct sum of the L2 modules, L2 of x mu I, is unitarily isomorphic to H. So this is unitarily isomorphic to H. And that's it. So this completes the proof. So we now see that H is unitarily isomorphic to L2 of omega mu. Okay, and as a corollary, we get a functional model for normal operators on a Hilbert space. Well, this will be Theorem 4. Theorem 4 is a functional model for normal operators. And actually, this is our first form of the spectral theorem. Spectral theorem 1. So suppose that H is a Hilbert space. And suppose that T is a normal operator on H. Then there exists a measure of space omega a mu, and there exists a bounded measurable function phi from omega to the complex numbers, such that T is unitarily equivalent to the multiplication operator by phi, to the operator m phi on and phi acts on L2 of omega mu, and it's just the pointwise multiplication by phi. Okay, so this is the functional model for normal operators, and actually this is a special case of Theorem 3, because if T is a normal operator on H, then H becomes a star module over the algebra of continuous functions on the spectrum by means of the continuous functional calculus of the operator. And if we apply our previous result, that is Theorem 3, we get the required measure space. And in fact, our function phi acts from omega to the spectrum of T. In particular, it is bounded. Okay. In fact, many people believe that this result is the optimal form of the spectral theorem. Well, actually, this theorem is indeed very useful. The obvious advantage of this result, of this form of the spectral theorem, is that this theorem is very concrete and understandable. So I mean that the statement is easy to understand. It is given in very concrete terms. And actually, all the essential information about our operator is contained in this functional model. On the other hand, the disadvantage of this function model is that it is not canonical in any reasonable sense. And the reason is that if we recall the construction of the functional model, we see that it depends on the decomposition of H, on the decomposition of H into Hilbert direct sum of cyclic submodules, which is not unique. So our next goal is to prove another form of the spectral theorem, which is related to the Borel functional calculus. Spectral theorem 2, the Borel functional calculus. The definition of the Borel functional calculus involves two locally convex topologies. So let's first discuss these topologies. They are called the weak measure topology and the weak operator topology. In fact, you may remember that we have already discussed the weak operator topology some time ago. And the weak measure topology is new for us. Let's start with the weak measure topology. So suppose we have a compact Hausdorff topological space X. And we consider the following two Banach spaces. We denote by B of X the space of all bounded Borel functions. The space of all bounded Borel functions on X. So it's easy to see that this is a Banach space with respect to the supremum norm. Simply because it's a closed vector subspace of the space of all bounded functions on X. And we will also need the space of all radon measures, all complex radon measures. On X. We know that this is also a Banach space. Let's now define a pairing between these two spaces. So the pairing is given by the following formula. It's given by the integral. So obviously this is this is a bilinear form, and it's easy to show that this form is non-degenerate. So we get a dual pair, B of X and M of X is a dual pair of vector spaces. The proof is a simple exercise for you. So now we define the weak measure topology. The weak measure topology. WMT on B of X to be the weak topology of this dual pair. This is the weak topology of this dual pair. So let's recall that explicitly this topology, because this is a special case of the weak topology, explicitly is given by the following family of seminorms. It's generated by the seminorms indexed by Radon measures and the seminorms are given by the following formula. So B of X equipped with a weak measure topology becomes a topological and becomes a Hausdorff locally convex space. By the way, it's a nice and useful exercise to describe the convergence of sequences in this topology. So useful exercise is to show that a sequence Fn converges to F in the weak measure topology, even only if it is uniformly bounded with respect to the supremum norm. And converges pointwise. The exercise is rather simple, but it involves two fundamental results. To prove the left to right implication, we have to use the Banach-Steinhaus theorem, that is the uniform boundedness principle. And to prove the right to left implication, we have to use the Lebesgue-dominated convergence theorem. Okay, we now have the following proposition. The proposition C of X, the space of continuous functions on X, is dense in B of X with respect to the weak measure topology. So it's instructive to compare with the norm topology. So if we equip B of X with the supremum norm, then C of X, of course, is not dense in B of X. It is a closed vector subspace, which is usually strictly smaller than B of X. But if we equip B of X with a weak measure topology, then C of X is dense in this space. The proof is a simple application of the duality theory, which was discussed sometime before. So first of all, we observe that the map from the space of Radon measures to the dual of C of X, which takes each measure to the integral with respect to this measure, is injective. Actually, this is the easy part of the Riesz-Markov-Kakutani theorem. Let's recall that this theorem states that this map is an isometric isomorphism, but the easy part is that this map is injective. So equivalently, this means that if we take the annihilator of C of X in our dual pair, then it is trivial. We take the annihilator in the dual pair B of X and M of X. Okay, now if we take a closure with respect to the weak topology, the closure of C of X in B of X with respect to the weak measure topology, so it follows from the general duality theory that this is the double annihilator This is a special case of the bipolar theorem. But since the annihilator is 0, we conclude that the double annihilator is B of x. And that's it. So we see that C of x is dense in B of x. Now our next goal is to show that the point mass multiplication on B of x is compatible with the weak measure topology. So we need the following definition. By definition, a locally convex algebra, is an algebra A, equipped with a locally convex topology, such that the multiplication on A is separately continuous. And here separately continuous means the following. For each element A in our algebra, the left multiplication by A, that is the map which takes B to AB, and the right multiplication by A, which takes B to BA. So both these maps are continuous. So this condition is essentially weaker than the usual continuity of the multiplication. But it turns out that there are many natural examples of locally convex algebras in which the multiplication is separately continuous, but is not continuous in the usual sense. Also, one more definition, a locally convex star algebra. A locally convex star algebra is a locally convex algebra A, a locally convex algebra equipped with a continuous involution. Okay. We now have the following result, proposition. The algebra B of x, equipped with the weak measure topology, is a locally convex star algebra. Well, when I say that it is an algebra, I mean that the multiplication is pointwise and the involution is just the complex conjugation. So it's obviously star algebra. So the proposition means that the multiplication in this algebra is separately continuous and the involution is continuous. To prove this result, we introduce the following construction. So for each bounded Borel function B, each bounded Borel function f on x, and for each Radon measure mu on x, we define a measure f mu on the Borel sigma algebra as follows: f mu of B will be the integral of f over b. So clearly this is a sigma additive measure. This is immediate from the properties of the integral. And it's a simple exercise that the absolute value of this integral is less than or equal to the supremum norm of f multiplied by the variation of mu of b. And this inequality easily implies that this is a Radon measure. F mu is a Radon measure on X. And one more simple exercise is as follows. If we take two bounded Borel functions f and g on X, then the integral of their product, where mu is an arbitrary Radon measure, is the integral of g with respect to the measure f mu. Again, this is a very easy exercise because if g is the characteristic function of a Borel set, then this formula holds by the definition of this measure. So by linearity, it extends to simple functions, that is, to measurable functions with finite set of values. And finally, by continuity, it extends to an arbitrary bounded Borel function g. Okay, so now by using this construction, we can easily show that the multiplication on our algebra is separately continuous. So if we take the pointwise product of f and g and calculate the respective semi-norm of their product, so this is the absolute value of the above integral. So this is the semi-norm of g corresponding to the measure f mu. And now from the general continuity criterion for linear operators between locally convex spaces, this equality implies that the map which takes g to fg is continuous with respect to the weak measure topology. Okay, and finally, to show that the involution is continuous. Well, this is the left multiplication by f, but obviously this algebra is commutative, so this readily implies that the multiplication is separately continuous. And to show that the involution is continuous, we observe that the semi-norm of f bar corresponding to the measure mu is the same as the semi-norm of f corresponding to the measure mu bar, the complex conjugate measure. And this equality easily implies that the involution is continuous. So it is a locally convex star algebra. By the way, a natural question is, how about the usual continuity, that is the joint continuity of the multiplication? The answer is a useful exercise. So the multiplication is jointly sequentially continuous, but in general it is not jointly continuous. Okay, now let's discuss the weak operator topology. Suppose now that H is a Hilbert space. H is a Hilbert space. Then by definition, the weak operator topology on B of H, on the algebra of bounded operators on H, is generated by the following family of semi-norms. The semi-norms are indexed by pairs of vectors in H, X and Y are in H, where this seminorm is defined by the following formula. Our next result says that if we equip B of H with the weak operator topology, by the way, the standard notation is WOT. So if we equip B of H with the weak operator topology, then this will be a locally convex star algebra. This is a locally convex star algebra. To prove this result, we take two operators, S and T on H, and we calculate the seminorm of their product, ST, corresponding to the vectors X and Y. So by definition, this is the modules of the following inner product, S, T, X, and Y. And this is the seminorm of S corresponding to the vectors T of X and Y. And this equality readily implies that the map which takes S to ST is continuous with respect to the weak operator topology. Well, now this algebra is, of course, is not commutative, so we have to show the continuity of the left multiplication. And this is also very easy because we can write the same expression, the same seminorm of the product in the following way. So we take S and move it from left to right. So we get the inner product of T of X and S star of Y. And this is the seminorm of T corresponding to the vectors X and S star of Y. And now this equality implies that the map which takes T to ST is continuous with respect to the weak operator topology. And finally, the continuity of the involution is immediate from the following relation. The seminorm of T star corresponding to X and Y equals the seminorm of T corresponding to Y and X. So this readily implies that the involution is continuous. And this completes the proof of our proposition. And by the way, again, as in the case of the weak measure topology, the multiplication of B of H with respect to the weak operator topology is not jointly continuous. And in fact, this result was already in the exercise sheet 2. So those of you who studied the weak, the convergence of shift operators in the weak operator topology know the answer. So the answer is that the multiplication on this algebra is not continuous in the weak operator topology, but it is separately continuous, and this is good for us. Okay, so that's all I wanted to say about the weak measure topology and the weak operator topology. So now we are ready to define the Borel functional calculus. So the construction of the functional calculus will be given at the next lecture, but today I'll give you just the definition. So suppose that T is a normal operator on a Hilbert space H. And suppose that K is a compact subset of the complex plane. And as usual, we denote by little t the inclusion map of K into C. This is the coordinate on K. By definition, the Borel functional calculus for T on K is a continuous unital star homomorphism gamma, or explicitly gamma T, from the algebra of bounded Borel functions on K, equipped with the weak measure topology, to BOH, to the algebra of bounded operators on H, equipped with the weak operator topology, such that gamma takes the coordinate little t to our operator T. So this definition may be compared with the definition of the continuous functional calculus. So the essential difference here is that now we require the continuity of this map, or this homomorphism, with respect to the weak measure topology on B of K and the weak operator topology on B of H.
Excuse me, do we identify functions which equivalent up to the measure 0?
No, because we don't have any distinguished measure on K.
Okay.
So K, we consider K just as K is just a compact subset of the complex plane. We don't equip it with a distinguished measure, and we consider all bounded Borel functions. So they are the same if and only if they are equal everywhere at each point. Okay, so this is our definition. Let's now look at some simple properties of the Borel functional calculus proposition. So suppose that gamma is a Borel functional calculus. By the way, at this point, a little correction in the usage of English. At this point, I probably have to put another article here. Because so far we don't know that it is unique. In fact, it is, but it is not immediate from the definition. Okay, so suppose now that gamma is a Borel functional calculus. For T on K. Then, first of all, we observe that gamma is continuous with respect to the usual norm topologies on these algebras. The supremum norm topology on B of K and the usual operator norm topology on B of H. And moreover, the norm of gamma equals 1. This is immediate actually from the fact that each star homomorphism from a Banach star algebra to a C star algebra is continuous and its norm equals 1. Second, we observe that the restriction of gamma to the algebra of continuous functions on K is the continuous functional calculus. For T on K. This is immediate from the definition. If we now recall the properties of the continuous functional calculus, we conclude that the necessary condition for the existence of such a homomorphism is that the spectrum of T is contained in K. Otherwise, there is no such homomorphism. And finally, we observe that if such a Borel functional calculus exists, then it is unique. Gamma is unique. And this follows from part 2 and from the density of C of K in B of K with respect to the weak measure topology. So we already know that C of K is dense in B of K, and since the continuous functional calculus is unique, this implies that the Borel functional calculus is also unique. So our next main result states that part 3, that is the assumption that K contains the spectrum of T, is also sufficient for the existence of a Borel functional calculus. Actually, we will prove, at the next lecture, we will prove a more general result about extension of star representations of commutative C-star algebras. So maybe let me just give you a statement of this result. This will be Theorem 1. Suppose that X is a compact Hausdorff topological space. And suppose that pi is a star representation of C of X on a Hilbert space H. Then there exists a unique continuous star representation pi tilde of the algebra of bounded Borel functions on X equipped with the weak measure topology to B of H, where B of H is equipped with the weak operator topology, such that pi tilde extends pi. So each star representation of C of X uniquely extends to a star representation of B of X, which is continuous with respect to the respective weak topologies on B of X and B of H. As a special case, this result contains the theorem on the existence of a Borel functional calculus. Theorem 2. Borel functional calculus theorem. And this is our second form of the spectral theorem. Suppose that T is a normal operator on a Hilbert space H. And suppose that K is a compact subset of the complex plane. which contains the spectrum of T. Then there exists a unique Modal functional calculus for T on K. So the Modal functional calculus is much richer and is much more interesting than the continuous functional calculus. By the way, let's recall that the continuous functional calculus exists for each normal element of each C-star algebra. For the Modal functional calculus, this is not the case. So it's very essential here that we work with the algebra B of H of bounded operators on a Hilbert space. If we replace here B of H by an arbitrary unital C-star algebra, then the result fails. So in conclusion, let's just observe that theorem 2 is indeed a special case of theorem 1. So to prove theorem 2, we simply apply theorem 1 to the continuous functional calculus. For T on K. So our plan for the next lecture will be, which will be our last lecture of this course, is to prove the above theorem 1, and then to deduce another, now the third form of the spectral theorem for normal operators, which describes normal operators in terms of so-called spectral measures on the spectrum. And that's all for today.